Is a qualitative description about Inviscid flow. So if you want to look at the thermodynamic process, you learn it in thermodynamics. We call it isentropic flow, right? So you have a fluid in motion, whether it's liquid or gas, and there is no heat transfer. Q net equals 0, mean there is net heat transfer, right? Is equal to 0, and then there is no friction work. Like flow in the pipe, you can see that there is a frictional work. For that case, the frictional work is not 0, so that is not inviscid flow. So this is the characteristic that you should remember about inviscid flow. Our goal here is to derive Bernoulli equation, and we're going to have quiz related to the Bernoulli equation. Right, let's say we have S coordinate system. Let's say S equal to 0. Here S approach infinity. Here S approach negative infinity. So if you learn about dynamics, you have seen this before, right? Let's say we have a particle here, and the particle punya motion, that's the velocity, and then that is the acceleration. The fluid is moving that, but it's decelerating, right? It becomes slower as it approaches as infinity. And if you want to evaluate the Newton's law, right? So this is the way that we write the equation. Summation of all force in S coordinate system equal to m a s. So this one is as, or this one is vs, right? So we another coordinate system that can represent the same, it will be the tangential normal coordinate system, right? Sorry, I shouldn't put A there. A also at the same position of the to define that. So we want to evaluate the Bernoulli equation based on this motion, and we're going to use open thermodynamics. You can also use closed thermodynamics to solve this problem. If you have the initial position, right, and this one is the final position, and this is a closed thermodynamic system. Right, so if I try to make it larger, so we have the fluid mass, and then there is a boundaries of the thermodynamic system, and this fluid particle receiving work, for example, from the body forces and the surface forces, right? Let's say we have a surface forces from pressure. C1 is P plus dP. This one is P. And then we have also P there, right? P, and the value should be different from that. But when we evaluate the S coordinate system, these two force due to the pressure is balanced, and we're not going to consider that in our calculation. And then we have the weight W. This one is doing work to our problem, right? And we're going to consider the weight in solving this problem if we are using closed thermodynamic system. So for closed thermodynamic system, we have an equation called energy balance. Right, energy balance is an equation. So it's an equation. It's come from the first law of thermodynamics. Right. So how we can get the first law of thermodynamics? This first law of thermodynamics comes from the conservation of energy. Right. So what is the conservation of energy? It means that energy is always can change form, right? Energy can change form. So this is what we understood, right? Energy can change form. Never said to me when I ask you conservation of energy, what is the conservation of energy? Energy cannot be created, energy cannot be destroyed. Don't, right? If I ask you in the test, I will not mark your answer because it's really disturbing for me to know that answer. So what you should say, conservation of energy, energy can change form. So what it means, we're going to see that later. And this statement cannot be solved, right? So we have to convert it into mathematical form. And this one is also being used in thermodynamics. We're going to call it as the first law of thermodynamics. So first law of thermodynamics says that the energy can change form. So, and we translate this statement into equation. So the equation will be delta E systems minus E in minus E out, right? So delta E will be the total energy of fluid, because we learned about fluid, right? If it's water, delta total energy change for water, and then one is equal to energy exchange. It can be heat, it can be work, it can be energy of the mass entering and leaving the boundary of the thermodynamic system. When we considered a closed thermodynamics, so there is no mass flow. So all the energy changes as the fluid is moved from this location to that location only contributed by the heat transfer and work transfer. Right, so we have Q net, heat addition minus heat loss minus work done on the fluid. Right, so there is various form of work, and some of them include expansion of the fluid. Let's say we have the fluid here, the dimension is 1 meter cube. So when it's flow to the higher position, the volume increasing, right? Let's say 3 meter cube, right? So you have a water tank size at your home, right? 1 meter cube, and then it raised to a certain location, it's expanding to 3 meter cube, as big as your room, right? So that we have boundary work, so the fluid is expanding. Now, so in our problem, when we solve to derive the Bernoulli equation, we going to set certain assumption. Now, what is the total energy change? Delta E is change of total energy. So what is the total energy? So total energy includes the internal energy plus kinetic energy plus potential energy, and then we have change because the fluid is moving from this position to the final position, so we have change there and change there. The unit will be in joule, right? In joule, and this one will equal to Q net plus work net. So we said just now that for Inviscid flow, there is no heat transfer, there is no friction, right? So this is what we already decided. So there is no Q, heat transfer, but there is a flow work, right? That the expansion of the system, right? So let's say we have P dV, right? So that is the expansion of the system, the work that caused the fluid to expand. And this one, for our case, we have that shape, right? And P is pressure at that particular location, right? So we have P, this one is P, so we have all the values are P at a point, right? Here P, this one P inlet, this one P outlet, right? So this one is P, P, P. Of course, at the point will be P, right? So we're going to remove this part, and we just represent that the pressure at that point at the initial location, the pressure is P, and then we have this dV, right? Like a balloon. So if you have pressure here, is also try to force the volume to expand, right?